Welcome to Lecture 14 of Vector101. This is a re-recording because the first recording did not come out well. And today we are going to take a bit of a side quest into invertibility. So earlier on Monday in Lecture 13, we talked about the determinant, we talked about eigenvalues, and again last week we also talked about eigenvalues and eigenvectors, but I think we said all I really wanted to say about eigenvalues and eigenvectors last week. So this week, this is kind of why we're taking a bit of a side quest, still slightly related, at least to the determinant. All right, so then today's agenda is we're going to recap a bit from Monday, and then we'll get into our story about invertibility, and then we will code inverting a matrix. And reminders, as always, to do the exercises. I think by the time you're seeing this, the solutions for this week's homework are actually already up. And then you've already missed office hours for this week. I apologize. But it's always on Saturdays at 1 p.m. Okay, so on Monday, we started out by talking about the determinant. And remember, determinant was our notion of the signed volume of the parallelepiped that the column vectors of the matrix form. And that was a lot of words in one sentence. I'm going to show you a picture of the determinant later in today's lecture. So on Monday we gave you this formula for the determinant because we don't like computing it because the formula is not great, but sometimes you have to. And this is the formula. We didn't tell you how to arrive at this formula. It's a little cumbersome, maybe. Like, kind of the way you do it is you say, I want this function. I want this determinant function to satisfy certain properties. So you state what properties it satisfies, and then from this you arrive at what the function is. But anyway, just gave it to you. And this is also only one way to compute the determinant. There are other formulas that give the same solution, but you compute them a bit differently. And just to hit you with some vocabulary that you might see on the internet if you're reading about the determinant. So on Monday, well, this one we already saw. We called this matrix here, where you remove the first row in the ith column, we call this the principal submatrix. And for your homework, you will be coding a function to get a principal submatrix. And then this one we didn't say, but if you take the determinant of your principal submatrix and you multiply it by this -1, the sign factor, this is called the cofactor. And then lastly, just this determinant on its own, this is called a matrix minor. And then due to this cofactor term, this formula for the determinant is called cofactor expansion. And so in homework 14, you will code cofactor expansion. All right, but what's so great about the determinant? Well, what we saw is that the determinant of a matrix determines if the matrix is invertible. So if the determinant of a matrix is 0, well, the determinant of a matrix being 0 is if and only if A is invertible. I butchered that phrasing. But like this is why we like the determinant, is it tells us when a matrix is invertible. And this is going to be one small part in a theorem we're about to see called the invertible matrix theorem. All right, and then lastly, on Monday, now that we have the determinant in hand, what it gives us is a way to compute eigenvalues. Because if you take the determinant of this a minus lambda I, you get what's called a characteristic polynomial, and the roots of this polynomial are the eigenvalues of the matrix A. So this is two reasons that we like the determinant. It tells us if a matrix is invertible, and it gives us a way to compute eigenvalues. Now we already had a way to compute eigenvalues. Last week we talked about the power method. What's nice about the characteristic polynomial is that one, you can compute it, well, for small enough matrices you can compute it reasonably by hand, and two, it gives us a way to compute all of the eigenvalues as opposed to just the largest one. All right. So now we have the invertible matrix theorem, and this is kind of going to be at the heart of today's lecture. It is a very large theorem, so it actually goes on to the next page. And before I get into it, well, let me tell you what it says. So given some matrix A given some n by n matrix A and some linear transformation T that represents, or A is the matrix that represents the linear transformation T. So given the setup, then the following 19 things are equivalent. Now the first one says that A is invertible, so everything else in the list is equivalent to A being invertible. Meaning, if A is invertible, then everything else is true. If A is not invertible, then everything else is false. And the same goes for everything else. So if condition 4, for example, is true, then again every other condition is true. And so this is a common form of theorem in math where you see a bunch of things that are equivalent. And it'll be even shorthanded sometimes to TFAE. The following are equivalent. And at least in my experience studying math, this theorem is uniquely long. However, my algebra professor once told me a story where in grad school he was studying a certain type of vector space called a Banach space. And a Banach space is a vector space where you have a notion of measuring distances and lengths, and also where there's a condition about certain sequences of vectors converging. But anyway, his advisor tasked him to go into the library and to research something about Banach spaces. And so he finds this book, and in this book, it is entirely filled with theorems just like this, where it's the following are equivalent, and then there are 47 equivalent things. And then it goes on to rigorously prove every single one of them. So just this tome of theorems about Banach spaces. So compared to that, this one seems small. But anyway, so the important one is that A is invertible, and what we saw on Monday is that an equivalent condition is when the determinant of the matrix is non-zero. And well, I won't go through all of them, but actually going through all of them is good to sort of test your knowledge. But really, actually, a lot of these are nearly the same thing. For example, look at number 5. So to say that the equation ax equals 0 has only the trivial solution x equals 0 is literally the same thing as saying that the null space of A is the set of just the zero vector. They're rewording. So I don't know if they really deserve 2 spots in this theorem. A bunch of them are like this. So it's less information than you think. All right, so we'll go on to the next page. And all right, so here's 15 and 16. So these are the definition of invertibility. So if A times some B gives you the identity, then necessarily B is the inverse of A. So okay, so of course A is going to be invertible in that scenario, and the same goes for the other. A times C equals the identity. And then these last 3 are what we're going to focus on now, which is that the linear transformation, the linear transformation is invertible, and then the linear transformation is injective and surjective. And these are not terms I've defined yet. I'm going to define them now. So okay, I won't say too much now. Let's just keep going. So now we're going to discuss invertibility in general, just for any function. And then once you know a little bit about this, we're going to talk about invertibility specifically for linear transformations. All right, so let's recall from, I think, week 2, that a function f, which maps from the set x to the set y, assigns each element in x to one element in the set y. And this part here, where we assign each element in x to only one element in y, is important. So, all right, so for example, each dot here on the left gets mapped to one dot on the right in y. However, look at this function on the right, where this dot here gets mapped to two things. And because it gets mapped to two things, f is not a function. And the reason we don't like this is because, let's say if I named this point a, and I wanted to evaluate f of a, well, it's ambiguous. Like a could go here or it could go here. And we don't know which. So we don't like that ambiguity, which is why that f is not a function. All right, whereas this one on the left, that's good. Now let's look at this one on the bottom right. Well, if we were in class, I would have asked you, is this a function or not? And maybe you should pause and think about whether these two on the bottom are functions, but I'll just tell you the answer, which is that this function on the left, or this line on the left is a function because each element on this x-axis gets mapped to one element on the y-axis. And often in your algebra class, you will use what's called the vertical line test to know if something is a function. So if I drop down a vertical line, my vertical line should only touch one thing. If it touches two things, then it's not a function. So if we look at our figure on the right side, we see that if we do our vertical line test, our vertical line touches in two places, meaning that this point on the x-axis gets mapped to two things, which makes this not a function. So not a function here, but good function there. All right, so now what does it mean for a function to be invertible? So a function is invertible so a function f from x to y is invertible if there is a function g from y to x such that g of f of x is equal to x for all little x in x, and f of g of y is y for all y in y. A lot of y's there. All right, so what you should notice is that this little x here that I'm feeding into f comes from the set big X. And so f maps this little x into the set y. And then g eats from y and spits back out into x. And so when we compose g of f of x, x just gets sent right back to itself. So we would say that g of f of x is the same as the identity function. We call this the identity. Kind of like an identity matrix, actually. Because the identity takes an x and it spits back out x. And then, furthermore, we need to be able to take in any element y into g, and then we feed it into f, and then we again get the original y back. And so this is also, and maybe I should, well, that's fine. This is like the identity of the set x and the identity, something like that. But both of these are the identity function. You put something in, you get the exact same thing back out. And that's our definition of a function being invertible. All right, let's look at some examples. So our example here We have a function f, it maps from R to R, and the rule of f is that we take an x and we cube it. All right, this function looks something like, pretty good, pretty good. So this is going to be f. And now the inverse of f, which pause and think about what the inverse of f is it is x to the 1/3. Actually, I think I want to put this in purple. And this function looks like that. This is f inverse. And then when you compose these functions, so when you do f of f inverse of x or f inverse of f of x, you get the identity function. The identity function looks like roughly like that. Here's the identity function. And what you'll notice is that like 0 gets mapped to 0, 1/2 gets mapped to 1/2, 1 gets mapped to 1, -1 gets mapped to -1. So this is indeed the identity function when you compose them. All right, good. So this f is invertible. Let's look at a function that is not invertible, namely the sine function. And if you don't know what the sine function is, that's okay. I'm just going to draw a picture for you, and that'll be enough. So sine looks, let's see, roughly like this. Now, why is this function not invertible? Let's take, for example, let's look at 0. So f of 0 gets mapped to 0. But also f of -pi gets mapped to 0. F of pi also gets mapped to 0. And so on. And actually, there are infinitely many things that get mapped to 0. So then when we go to construct our inverse, we want to say like f inverse of 0. Well, what should be the inverse of 0? Well, we want to know what gets mapped to 0, but the issue is that multiple things get mapped to 0 because f maps 0 to 0, it maps -pi to 0, it maps pi to 0, and so on. So there's no clear inverse for 0. It could be any one of these infinitely many inputs. Right, so we don't know how to take 0 back to an input. And actually the same goes for any number between -1 and 1. There are infinitely many inputs that map to each number in -1 to 1. So this makes f not invertible. Now, if you're familiar with the arcsine function, well, the arcsine function is kind of like an inverse. Where with the arcsine function, what we do is we limit our view to this box here. And so if you don't consider anything out here or out here, well, now our function, oops, if we look at just this part, then it is invertible. And that's what the arcsine function does. But again, so like f in its totality is not invertible. Okay. So we know what it means for a function to be invertible. And right now, if we want to know that a function is invertible, we have to like literally construct the inverse. Like I only know x cubed is invertible because I know what its inverse is. But otherwise, I don't know. Like if I didn't have the inverse, I wouldn't know. So that's what we want to do now is find some criteria to know if a function is invertible. All right. So surjectivity. A function f is surjective, or also onto, if every element in y gets mapped to by an element in x. And mathematically what we say is that for every y in y, there is some x in x such that f maps x to y. So everything in y gets mapped to. And I'll look back now. We'll look back at some of our examples here. So an example of a surjective function, well, so this one up here in the top left, this one is not surjective because we see that two dots here don't get mapped to. And again, this one is also not surjective because this dot doesn't get mapped to. However, in the bottom left, this one is surjective because every point in the codomain gets mapped to by our function. Now let's look at our functions here. So the sine function is, or let me look at the bottom left first. X cubed, this one is surjective for the same reason that, well, we're kind of just looking at the picture. It's actually like almost the same picture as the last slide. But everything in the codomain gets mapped to, whereas the sine function is not surjective because we only map to the range of -1 to 1. All right, this is surjectivity. Second, we'll talk about injectivity. So a function f from x to y is injective, or 1 to 1, if no two elements in x map to the same element in y. Mathematically, we say that if x1, which is not equal to x2 in x, then f of x1 is not equal to f of x2. So we're saying that if two elements are not the same, then they must not map to the same thing. And then an equivalent way of saying this is that if f of x1 is equal to f of x2, then necessarily x1 is equal to x2. All right, let's look at some examples of injectivity. I'm not sure if I put any on here. Okay, so this function, this is injective because no two dots in x map to the same thing in y. Everything gets mapped to its own thing. And okay, so this function down here in the bottom left, this one is not injective. And the reason it's not injective is that every point along this segment here gets mapped to by multiple things. So if I said that this was like maybe 1 here, well, 1 gets mapped to multiple times. It gets mapped to by, I don't know what these points are, maybe 1 and 2. So multiple things map to 1, so this function is not injective. And let's see, this one in the bottom left, this one is injective. And sine is not injective, which we saw before. Like multiple things get mapped to 0. All right. Now, if you combine these two things, surjectivity and injectivity, you get bijectivity. So a function f from x to y is bijective, or we say in 1-to-1 correspondence, if it is both injective and surjective. And the point is this claim here, which is that a function is invertible if and only if it is bijective. And the proof for this uses my very favorite proof technique, which is assigning it for homework. So this is on homework 14. Optionally, you can prove this. Okay, but the point of all of this is that previously we had to construct an explicit inverse to know whether a function was invertible. But now we only need to check two conditions, and those conditions are surjectivity and injectivity. Because if a function is both surjective and injective, then it is bijective. And what we claimed on the last slide is that being bijective is equivalent to being invertible. And so if a function fails to be surjective or fails to be injective, then it fails to be bijective, and so it fails to be invertible. So now we have these two conditions that we can check to know if a function is invertible. All right. Now let's finally talk about linear transformations. So everything we've said up until now is true for any function in general. But we want to know how this applies to linear transformations in particular. So I pose the question to you: when can a linear transformation T from Rn to Rm be surjective? And I've broken this down by cases for n and m. And I don't have an audience today, so you should pause and ponder this for yourself. I will proceed to give you the answers now. So what do we think? When n is equal to m, do we think a linear transformation could be surjective? All right, so the answer to this one is yes. And an example is a linear transformation that just scales every point. So if you took every point in space and you scaled it by 5, well, our function still hits every point in space. I think I said that right. All right, so a linear transformation from Rn to Rm, where their n and m are equal, can be surjective. Now, I'm not saying that it has to be surjective. I'm just saying it could be surjective. All right, so what if n is greater than m? Well, here the answer is yes. And the way that I'd like to think about this is that what we're doing is we are taking some bigger space, Rn, and we are crushing it up to fill up some smaller space, Rm, because remember, n is greater than m here. So we're crushing a big space into a small space, and so naturally we kind of think that we must, our function must hit everything in this small space. Again, it doesn't have to, but it could. And then if n is less than m, then the answer is no. And the way I think about this is that we are now mapping some smaller space, Rn, into some bigger space, Rm. And so our smaller space fails to fill up our bigger space. There's like some wiggle room there. So it could not be surjective. Meaning our answer is that a linear transformation T from Rn to Rm is surjective, or could be surjective, when n is greater than or equal to m. Now let's think about injectivity. So when can a linear transformation T from Rn to Rm be injective? So let's think about first when n is equal to m. And, well, we can actually think about our previous example of just scaling points. If all our function does is take points in Rn and it scales them, well, no two points are going to map to the same point. And so, yes, this could be injective. And I've used the same example. However, if n is greater than m, then the answer is actually no. The way to think about this one is that we are mapping some bigger space into some smaller space, and so naturally things are going to get crowded. And by crowded, I mean multiple points in Rn are going to map to the same point in Rm, meaning it won't be injective. But if n is less than m, then yes, it can be injective. And here what we think about is that our smaller space Rn getting mapped into our bigger space has lots of wiggle room. And so the points in Rn don't have to map to the same point in Rm. We can avoid those collisions. And so it looks like I forgot to erase my answer here. The answer is that a linear transformation from Rn to Rm can be injective when n is less than or equal to m. All right, so notice T can be injective when n is greater than or equal to m. Sorry, did I say injective? T can be surjective when n is greater than or equal to m. And it can be injective when n is less than or equal to m. So T can only be bijective when n is equal to m. And hence, only square matrices are invertible. Okay, so I'll repeat that one more time. A linear transformation T from Rn to Rm can only be bijective when n is equal to m. And we said that being bijective is an equivalent condition to being invertible, meaning T can only be invertible when n is equal to m, and hence the matrix that represents T can only be invertible when n is equal to m. So only square matrices are invertible. Okay, now if you wanted to formalize this, you would appeal to what is called the rank nullity theorem. And I think this theorem was at least verbally mentioned previously. I'm not going to prove it to you. All it says is that given some matrix A, so given some m by n matrix A, the dimension of the column space plus the dimension of the null space must sum to the number of columns n. So I get, okay, so maybe formalizing is a bit strong because there are some things on the slide that are still unproven, but I claim that T is surjective when the dimension of the column space is n. And I claim that T is injective when the dimension of the null space is 0. So then what you should notice is that both of these only happen when A is square. Because, let's see, when A is square, it can happen, it can happen that the dimension of the column space is n, and necessarily then the dimension of the null space must be 0. They sum to n. Okay. All right, so then a corollary from this is that, well, I guess what I just said. So a linear transformation from Rn to Rn is surjective if and only if it is injective. Okay, so I think on the last slide I actually explained to you not what I meant to explain to you. Here's what I meant. When T is surjective, the dimension of the column space is n, and due to the rank nullity theorem, necessarily the dimension of the null space must be 0. That is to say, when T is surjective, it is necessarily injective by the rank nullity theorem. And conversely, if T is injective, then by the rank nullity theorem, it is necessarily surjective. So then, a linear transformation from Rn to Rn is surjective if and only if it is injective. So this is kind of powerful now. The upshot is that to know if a square matrix is invertible, we only need to check one of these two conditions. We only need to check whether the dimension of the column space is n, which was surjectivity, or whether the dimension of the null space is 0, which was injectivity. Right? So in general, to know if a function is invertible, you have to check both conditions. But what we've seen by the rank nullity theorem, there's something special about linear transformations where you actually only need to check one of them. Because if you know whether one of them is true, then the other is true. And if you know one of them is false, then the other is false. So we've like halved the amount of effort that we need to put in to know if a linear transformation is invertible. And finally, we are now going to compute the inverse of the matrix. And the thought is now just occurring to me that the way we're going to compute it is to, I think it's correct to say that we're going to check whether the dimension of the null space is 0. Or well, it's sort of implicit in the way we compute the inverse. But that's the one that we're looking at of the two. All right. So what does it mean for a matrix to be invertible? Well, again, so we said earlier that a matrix, that only square matrices are invertible. And what it means to be invertible is that there is some other square matrix B such that AB is equal to BA, which is equal to the identity. And this mimics what we saw for functions. So we saw for functions that like f of g of x is the identity, and that g of f of x is the identity. And so what we have here for matrices is very similar. All right, and the way we're going to compute the inverse is we're going to take a matrix and we'll augment it with the identity. So we'll have A, and then we'll augment it with the identity. And then what we're going to do is we're going to try to row reduce A to I. And as we row reduce A to I, we're also going to row reduce I to B. And if we're able to bring A to the identity, then B is the inverse of A. So the way to think about this is like if we have A, then if it's invertible, B is going to take it to the identity. So if we do our row reduction and we bring A to the identity, then this B records everything that we did. It records all of the information we need to bring A to the identity. And that's why I'm saying that this B is the inverse of A. This is our algorithm. And so if you try to row reduce A and you don't get the identity, then A is not invertible. Briefly, I have an explanation of why this works. Now we saw from lecture 10 that row reduction can be accomplished using matrix multiplication. And so if we have a matrix A and we want to bring it to its reduced row echelon form, we can actually use these elementary matrices to bring it to its RREF. But I didn't really like justify why you can do this, so I won't dwell on it too much. But okay, so here it is spelled out. When we do a row reduction and we're able to take A to the identity, what we're doing is we're taking A and multiplying by these elementary operations. So we multiply by R1, we multiply by R2, and so on down to Rn, and this gives us the identity. So what we notice is that we group these matrices here. We have some matrix times A, which gives us the identity. Meaning the inverse of A must be these matrices here. So A inverse is going to be the product of these elementary operations. And the reason our algorithm works is that all of this information gets recorded by the adjoined, or not adjoined, I should say augmented, by the augmented I. So when we augment A with I and then we row reduce, what we're doing is we're multiplying A by these elementary operations, but we're also multiplying I by these elementary operations. So at the end, what we're left with is this part goes to I, and this part goes to A inverse. Or rather, well, sorry, these are equivalent. Yeah. Okay, I'm running low on time, so I'm going to now switch over to code. Right, I promised at the very beginning that I would show you a picture of what the determinant looks like. So here is that picture now. What you're looking at is our favorite demo of the entire course, which is to look at the columns of a matrix. So there's green, blue, and red. These are the columns of some 3x3 matrix, and the determinant is the signed volume of this shape here. And if let's see, all right, so now we can sort of see what this shape is doing. And by the way, this is you're looking at like the unsigned volume, because I don't, my demo does not indicate when the volume is negative. So the determinant is the volume of the signed volume of this parallelepiped. And you could try to derive the formula for the determinant geometrically by trying to derive the volume of this parallelepiped, but it's very hard. I've watched somebody try to do it. It's they did not succeed, but it was a valiant effort. Yeah, so that is the determinant. But what we came to do today is to code inverting matrix. Make sure. Okay. So first I have some updates on our code, which is that you'll no longer see the eigensolver code and the system solver code. That's because I stuck them in the matrix class. We were, had I not done that, we would have run into a circular dependency today. So now, let me find them. Yeah, here we go. So here's the row reduction code. This I just stuck into the matrix class. It's all the same code as before. And then this was, I think, a homework solution, ended up in here. I think, again, this might have been a homework solution. And then here was our power method code from last week. All right. And then what we're doing today is we're computing an inverse. Yeah. So what did we say our algorithm was? Well, first thing what we should do is we should assert that our matrix is indeed square. And then we said that we augment our matrix with the identity. So we're going to create an augmented matrix using our augment with method. And we'll augment it with the identity. And then we're going to row reduce this. And now because I have moved our system solver code into the matrix class, I can just call this row reduce method directly on our matrix. And now what we want to do is know if our reduced matrix, right? So we want to know if the left half has reached the identity. So remember, it's like, all right, so what we did here is when we augment, we end up with something like A augment B. And then when we row reduce, our goal is to get something that looks like A augment I, and then we want to end up with I augment B. So we have to make sure that the left half of our matrix now is the identity. And to do this, to grab the left half, I have prepared a sub-matrix method. And so I'm just going to paste it in here. We're not going to go through it, and you're free to copy it yourself and use it in your homework for free. But all of this does is it gets a sub-matrix of a matrix. So we specify the top left row, the top left column, the bottom right row, and the bottom right column. And this will give us a sub-matrix. So in our case, the sub-matrix that we want, the left half, we want to start at the top left. So 1, 1. And we want to end in the bottom middle. So that will be, we want to end in the bottom row and then the middle column. So this gives us the left half of our reduced matrix, and then the right half, we're going to again start in the top row, but now we're starting on the right half. So this is going to be self.rows plus 1. And then again, we want to end up on the bottom row, and then we want the far right of the matrix, which is twice the number of original rows, right? Because if our matrix is n by n, then the augmented matrix is n by 2n. So we want the 2n column. All right, so this is the left half and right half of our reduced matrix. And all we're going to do is, so if the left half is equal to the identity, then we know our matrix was invertible and that the inverse was the right half. Otherwise, we're going to return nil. And I'm just about at time. So very quickly now, I'm going to paste in one more function, and this will let us run some test cases that I've prepared. So the last function I'm going to paste in here is called the Frobenius norm. And the Frobenius norm is an analog of the vector magnitude for a matrix. So there are many ways to quantify the magnitude of a matrix. The Frobenius norm is just one of them. And what I like about it is that it's just the like simplest, fastest one to compute. And so what the Frobenius norm will let us do in our test cases So in our test cases, we have some matrix, and we have like the expected inverse, what we know to be true, and then we're going to compute the actual inverse using our method. And so we're going to use the Frobenius norm for is to know if our computed result was close to our expected result. It's the same thing as if we were to do like if we wanted to look at if two numbers were close, we would look at if their absolute value was less than some small number. If we wanted to know if two vectors were close, we would look to see if the magnitude of their difference was some small number. And so similarly, we are looking at if the Frobenius norm of our expected inverse and our actual inverse is small. And if it's small enough, then we were like reasonably correct with our inverse. All right, so let's hit run on this. Oh, I should have showed you. So this data here these are just some test cases. So like the matrix is the identity, and its inverse that we're expecting is also the identity. Here is just some random matrix I generated, and its inverse we expect to get this. So these are our test cases that we're checking against. So now I'll run this, and we'll see how we did. Okay. A lot of things in the aha. Okay. What do we see? So we see we put in the identity matrix. We expected the inverse to be the identity, and what we got was the identity, so we passed the test. Here's another matrix. Here's the expected inverse, the actual inverse. Good. All right, these are looking very good. All of our tests are passing. Okay, and so down here, we have some matrices that are not invertible. So this matrix is not invertible. We expect the result to be nil, and indeed, we got nil. And same for the rest of these down here. This random matrix is not invertible, and we got nil. So there you have it. That is computing the inverse of a matrix. That is the end of our side quest. And now next week, when we talk about affine geometry, we will be actually talking about affine geometry in the code lecture. All right. So thank you all for watching.